Welcome again, Vitas, to a new lesson. In the previous parts of this lesson, we saw how rotations apply to vectors in index notation. Now we are going to talk more about vectors because they are really important. Well, in all physics, vectors are really important, but more in general relativity. So we are going to introduce Greek indices also because we are going to start like generalizing some other things because we have been working only with 3 dimensions. So we are going to treat vectors which may be n-dimensional. We are also going to introduce like general transformations for vectors, and also we are going to introduce a really key idea, which is that it's not really trivial to grab two vectors and compare them. So let me start by showing you this image. This image is from Carroll's book of Introduction to Spacetime, and well, here you see manifold, but you can just think of this as a surface because we haven't seen manifolds yet. We are going to see them in another lesson. Now I want to bring here our friend R2, which is the usual coordinate system, x and y, in flat space. So let's say that we have two particles. Okay, we have a particle which is moving with velocity v1 and another particle which is moving with velocity v2. Now you may ask yourself, how do I compare the velocities of these particles? Well, we know both vectors of the velocities. So we may drag one vector around. So let me write here a little path. We may drag this vector to the vector v1, and now we can add the vectors, or we can subtract them, or we can do anything with them. We can operate with them. Okay, so this is very trivial, okay, because we do this all the time in physics, in classical mechanics. But in general relativity, this is much more complicated. So look at this image, and let's say that we have a vector, well, a particle at point P moving with this velocity, v1. Okay, first of all, the particle is confined to the surface, and as you may know from classical mechanics, if you have a particle which is confined in a surface, or for example, in uniform rotational motion, the velocity of the particle is tangent to the circle. So the velocity of the particle here at the surface is going to be tangent at the surface. We can build a tangent plane, which is this one that is presented in the image. And well, we just need two vectors, which are these, which are drawn in black. We need two vectors which act like a basis, and then we can expand any other vector, such as v1. So we can expand v1 in terms of these two basis vectors. So we have defined a tangent plane at point P in order to define the velocity v1. This is really important because if you think about it, this plane, this tangent plane, is like R2. These axes are like x and y. So now let's say that we are going to go to point Q, okay, which is here, for example, point Q. And at this point there is another velocity, there is another particle which is moving at a velocity v2. So how do we write the vector v2? We need to define another tangent plane here. We may have some other basis, so we can have this vector and this vector as a basis for the tangent plane. And now if we want to compare the velocities, what do we do? Because here in R2 we could grab a vector and move it around. So the question is, can we move around vectors in a cubed surface? Let's do an example. Here we have a sphere. Let's see. Well, as you may check, my drawing skills are not very good, but I hope you get the idea. Okay, so let's say that particle 1 is here, moving with this speed, well, this velocity v1, and particle 2 is here, moving at velocity v2. Let's say that we want to compare the velocities by summing them up. Okay? Well, if we want to sum the velocities, we may do as in R2, and we can grab the vector v1 and we can drag it around here. And now we have the vector v1 with v2. So from this, we can see that v1 and v2 are collinear, so they are going to be summing in one direction. Okay? But we can also say, no, I don't want to choose this path. Let's move the vectors in other way. So I'm going to follow this curve, and I'm going to pull v1 upwards, so that when it arrives at the top, it's going to be pointing in that direction. Okay. So if you don't really see this, you can imagine that if you are looking at the sphere from the front, being this the black line, what we are doing is just we are pulling the vector upwards, pointing always in the same direction. Okay. Now we are going to do the same with v2. So we have v2 here, we have v2 here, and now when it arrives to the top, it's pointing in this direction. Okay, so do you see that in the first situation we had v1 and we had v2 pointing in the same direction, but now here at the top of the sphere we have v1 pointing to the right and v2 pointing upwards? What do we do? How do we sum the vectors? The sum of the vectors, the comparison between them, depends on the path. When I first learned about this, this was completely mind-blowing for me. Because how does it make sense that comparing vectors depends on the path that you drag them around? We are so used to working in R2 that vectors don't really matter how we drag them or where they are, where are the origin, that we don't really take this into account. But in general relativity, this is very important. Because you also have to think about vectors not as arrows that span or stretch from one point to another, but just as something that lives in a single point. So all these vectors that are in this tangent plane, they do not live like in the plane, they live at point P. They are all defined in the point P, so they do not stretch out from the surface or anything. They live in the point P, and this is really important for general relativity. Some of you may think, wait, you are cheating. In this example, when you drag the vectors around these cubes, you are changing the vectors. You can simply grab the vectors, put them in the north pole of this sphere, and they are, as in the first example, they are collinear. Okay, so you are thinking in R3. You are not in R3. You are in a sphere. You are confined to the surface of a sphere. You live in a 2D world. The problem of this is that we represent these surfaces in a 3-dimensional space. But you really have to think, you have to put some imagination, that you live in a 2D space which is curved by any means or however it may be curved, and that when you transport a vector through a path, the vector changes. So from the 2D view, it seems like magic, because you are dragging the vector and it spontaneously begins to change along the path. If we are in a higher dimension, such as in this example, observing the lower dimensional surface, we know that what's really happening is that because the vector is confined to be in a tangent plane, the vector is going to keep going in the tangent direction of the curve. So at every point in the curve is going to be tangent to the curve. So that's the reason the vector changes when it's being dragged along the curve. And again, All of this happens because we are not in R3. We are in a two-dimensional space. Here we have 3 dimensions because we have made up a third dimension to represent the sphere, but it doesn't exist. It doesn't exist. All the vectors here, they live in the 2D space. So we cannot drag a vector and it suddenly points outwards, because it can't. Because it's a 2D vector and it has to be a tangent vector because it lives in the 2D space. The third and the higher dimension that we have built here to represent the sphere, it's completely made up by ourselves. So I highly recommend reading this paragraph. It's from Carol's book, and it addresses some things that we have been talking in the video, such as that the vectors are only located at points. We cannot draw curves such that we can drag vectors. And this last thing that I talked about higher dimensional external space, which we don't need because it's something that we make up to represent all these curves and spaces. So I'm going to divide the video in two. The second part is going to be another video, and I'm going to put in the description the link to go to the second part of tangent vectors. If you have any doubt regarding what we have seen here, feel free to go to the comment section and you can ask and I'll answer. So thank you very much and see you in the next lesson.